Recording in progress.
And please go ahead.
Okay. So hello everyone. So astrophysical as ultra-strong lasers, and as I understand, the audience here is a little bit of a mix of astrophysics and plasma physics, and a little bit of lasers. So I will try to reach to everyone. And also there may be a technical problem when later I may have to switch to my laptop. And this is the work that we did. Mostly, it was based on a work that we did with Victor, who is a professor here, and we posted this last week on archives. So, for the last there has been very interesting progress in what is now called astrophysical fast radio bursts. And this is a serendipitous discovery, and here is the original image, or not image, the frequency versus time plot, and we see the signal propagating here, and it's propagating from high frequencies to low frequencies because of plasma dispersion. And by the shape of this curve, you can determine what is called dispersion measure, meaning density times distance to the source. And if you, since people know where this source is, it was high up in the galactic latitude, meaning the dm meant that this burst came halfway across the visible universe. And the burst, if you disperse it, is just 1 millisecond long. So what we're dealing with is a very strange example of coherent radio emission that is so bright that very short, 1 millisecond, and it is so bright at this as traveling halfway across the universe, we still can easily detect it, and that raises a lot of plasma, astrophysical plasma, and laser questions that I will highlight. So since the discovery in identification in 2007, they are very frequent, about 10,000 per skies. At first, people thought they may be related to neutron-star mergers, but no. Some of them repeat, and the first repeater was identified in 2015. And since we know the repeater, people could follow up radio observations with optical, and indeed they found a host galaxy, and that host galaxy was indeed halfway across the universe. That means we're dealing with huge energies in radio, meaning peak luminosities as billion solar luminosities, but for just 1 millisecond. And these are very interesting physical constraints that I am trying to kind of understand. There is a lot of interesting observations. For example, they call it sad trombone, which means that, so this is frequency and time, and the signal goes down in frequency with time. Big breakthrough occurred in 2020 when a weak fast radio burst was observed from a galactic neutron star, a magnetar, highly magnetized neutron star. And what is plotted here, this is X-ray signal, and this is radio peaks. And as you can see, radio and X-rays correlate to within a fraction of a second. So radio and X-ray came within a fraction of a second. So you see, these are seconds, tens of milliseconds. So that identified, so this burst was much weaker than cosmological, but otherwise it looks like those super powerful, bright cosmological bursts. So this identifies connection between this class of neutron stars, magnetars, and these fast radio bursts. And since then, there were a few interesting discoveries. There are many repeaters, few dozens now. Might be periodicity, but actually just a few weeks ago, they said that it's probably not. And then there is interesting polarization swings through the burst. And those polarization angle swings remind what we see in normal radio pulsars. So here is what we're dealing with. There's a millisecond radio pulses coming halfway across from the observable universe. They're related to supermagnetized neutron stars. Supermagnetized meaning that our magnetic field can be of the order of the quantum field, 10 to the 14 Gauss, 10 to the 10 Teslas. Peak power, 10 to the 34 watts. And this I'm doing it specifically for lazy people who think about watts and watts per centimeter squared. A naught of interest can be in the millions. And this parameter A naught is a very important one. It's called laser nonlinearity parameter. So this is charge, electric field in the wave. So this is force. 1 over omega is time. So force times time is momentum. And then we normalize it by MC, mass of electron times. Meaning, if A naught is smaller than unity, then a zeta velocity of a particle in the electromagnetic wave is much smaller than speed of light. And for A naught larger than unity, the zeta velocity of a particle in a wave becomes relativistic. Okay? And for us, this A naught can be in the millions. The best laboratory lasers can produce up to 100, but it's cheating a little bit because they can do up to 100 in a very small point, basically. But 1 or 10 is regular. Still, here we're dealing in the millions. Also, in our case, the fluctuating field of the wave can be larger than guide field. Then we're dealing with spare plasma. That, as we will see, is a big difference.
I'm sorry, can I ask? Sure. So when you give A naught, what is that electric field? Is that of one wave? Or
of a wave, yes.
Not the sum of many waves? Or
this assumes that we're coherent in a pure state. So in principle, you can do it as a square root of intensity. It will almost the same, but yeah.
So you mean the fluctuation is compared with 10 to the 14 Gauss?
Yes.
Oh.
Well, not really, because this, no, not to the 14 Gauss, because this 10 to the 14, but then it goes r to the minus 3. Oh, so I will have a plot that shows relative these parameters. So basically, it may start from much smaller than unity, but then within the magnetosphere grow to much larger than unity, because the field of the wave goes as 1 over r, and the guide field goes as 1 over r cubed. So their ratio increases as r squared very fast. And then we can compare the guide field with the carrier frequency, and this is much smaller, maybe much smaller than unity deep in the magnetosphere, and much larger further out. And these two last points are the most important ones that differ from the laboratory, from lasers and from the laboratory plasma. In laboratory, you cannot create such large magnetic fields. For typically lasers are microwaves, and you need about 1,000 Tesla 10 to the 7 Gauss fields to match the frequencies, which is, you can, but it's not easy. Then we can be dealing with ultramagnetized medium, where the ratio of the magnetic energy density to the rest mass density is much larger than unity. In this regime, magnetic field becomes heavy. It's a very strange regime, and all the inertia may be dominated by the magnetic field. Finally, the wave may start inside plasma. So you may imagine that some coherent process generates this strong wave, but this coherent process occurs inside plasma. Then, as for example, plasma expands or flies out, the parameters change, and something else interesting will happen. But this is setup is very, very different from laser experiments, where it's always the laser pulse comes from outside into the plasma. Okay.
Yeah, the previous slide showing there's X-ray and gamma ray. Do people also observe optical curves?
No.
Not looking or
no, because usually radio, overall in astrophysics, radio and X-rays are very much related to each other because they are produced by non-thermal particles. So for example, pulsars, they produce radio emission, they produce X-rays and gamma rays, and only two pulsars produce non-thermal optical. In optical, usually in astrophysics, people observe thermal processes like the sun. But radio and X-rays, non-thermal, highly correlated over not only in pulsars, but in all parts of astrophysics. If there is X-ray detection, people always look in radio. If there is a radio detection, people always try to look in X-rays. Yeah. Good. Yes, so there are several questions. First is generation, and second is propagation. And in generation, we can ask where from, and this is more or less what do observations tell us. And there is a discussion, and I highly in favor of what's called magnetospheric events, meaning you have this some neutron star, there is dipole magnetic field, and somewhere on the magnetosphere something happens and produces this radio pulse. Another line of research goes for the wind models further outside. Then how to make these pulses? There is the energy, because they do use, very unusually for radio, these sources use a lot of energy. But then if you have neutron star with quantum magnetic field, there is enough magnetic energy that you need about a football field of energy, well, 100 meters cubed of energy, of magnetic energy to power. And the energy then should go through particles, because it's particles that emit, and then somehow coherent emission is produced. And I will, if I have time, I will discuss this a bit later, but now I would like to concentrate on propagation and escape. So let's assume we created a very strong pulse. And then we'll ask ourselves, can this pulse escape, or will it be absorbed? Okay. And by the way, so this is the laser parameters inside the magnetosphere. So this is radius over radius of a neutron star. This is my parameter A naught. It may be as large as few millions on the surface, and it goes as 1 over r. Then this is omega b over omega. It goes as 1 over r cubed. Okay. And then this is this parameter delta, which is a ratio of the fluctuating field in the wave to the guide field. And it becomes of the order of unity somewhere 100 stellar radii, and it may grow up to a few thousand. Okay. So large variations, and if we produce waves here, they start in one regime, they propagate through a different regime. So very rich system. Okay, and here is our main result, which I call Anderson's self-localization of light in paraplasma. Very surprisingly, we find that mildly nonlinear, A naught much smaller than unity, 10 to the minus 2. Well, typically we do 10 to the minus 2. Electromagnetic wave is underdense. Underdense means omega much larger than omega plasma. Pair plasma. Pair is the main thing. Cannot just propagate. And just meaning something interesting happens. And this talk is based on two publications, well, two submissions so far. Me and Victor last week, and also for a few weeks I was working with the team in San Diego, where we were concentrating specifically on large A naught limit. Okay, so in plasma physics, we all know dispersion relation. Okay. Omega squared is Kc omega. Omega plasma squared is 4 pi NE squared over ME. Okay. And you need a frequency larger than plasma frequency for propagation. And one would think that in pair plasma, all you need is 2 here, because the density will be 2 times higher. Okay.
Sorry, what is P prime here? Or omega P prime?
Comma.
Oh, sorry. Okay. Got it.
Oh, no, yeah, it's comma. Yes, yeah. Okay, yeah, it's omega plasma. It's comma. Yes. Also, there is a solution for nonlinear waves. With arbitrary A naught, and basically this says that perpendicular Lorentz factor goes approximately of 1 plus A naught squared. So it's a solution in Soviet physics, plasma physics in the 50s must be right, and it is right, but there is a subtlety.
So, sorry, A0 much less than 1, does it automatically satisfy that omega should be much greater than omega p, or it's
No, there's a different. Omega over omega p, it's a condition on frequency versus plasma frequency. And A naught is the strength of the wave. All the linear waves basically are expansion in A naught goes to 0. But if A naught is close to unity, the plasma starts to move relativistically in the field of the wave. Okay. And here is an example. So I am doing peak simulations, and this my plasma occupies from 0 to a few thousand wavelength, and I am shooting a pulse from the left, and the blue dashed is electron ion plasma, and A naught is 10 to the minus A naught is 10 to the minus 2. And I'm shooting kind of a pulse, trapeze pulse, and sure enough, the pulse travels through. Here, omega much larger, omega plasma. Somehow the picture shifts a little bit. Anyway, everything as we expect.
This looks like an electromagnetic wave.
It's yeah. So what is the Poynting flux? So this is what I am injecting on the left, and the pulse propagates as it should. Okay. And then if I do it, so the black dashed is electron ion plasma. So this is the pulse that I shoot an electron ion. But this blue line is, okay, I will need to switch. Sorry about that. Well, actually, let me go on until we run out of juice, and then we'll change.
So you have a uniform plasma.
Uniform plasma, pair plasma. Okay. And as you see, the electron positron started to propagate, but then it was cut off. And if you look at the Poynting flux, behind the pulse, it's all negative. Electromagnetic waves are reflected, propagate, the energy propagates back to the injection point. Okay, so again, this is and this is n over n critical 10 to the minus 2. So omega 10 times omega plasma.
And what did this look like earlier in time? Did it look like the black death?
Okay, so here I'm comparing, again, blue is electron ion, red is electron positron. And in the beginning, everything looks very similar. So this is T1, T2, T3. But then as the pulse propagates, the head of the pulse behaves as it should, but the tail is cut off. And as you can see, it's all kind of reflected back.
That's just large furthergoing paraplasma.
Sorry?
That's just very large furthergoing paraplasma.
Brilliant scattering, you mean?
Yeah, yeah.
It's kind of related, but not exactly, because I'm shooting into cold plasma here. Okay.
And it's like how cold?
Well, I'm shooting into the cold. It's getting heated a little bit due to numerically, but very little, very little. I will, yeah, okay. Yeah, but it's in that direction. Yes, it's kind of related to stimulated Brillouin scattering. So, and here I'm shooting a long pulse, so thousands. And what we see is so red is Poynting flux, blue is density. So we see that little nose of the pulse propagates, but then there is dark region. There is no energy less here. Poynting flux is 0. And you can check that it's not only Poynting flux, because Poynting flux could be 0 due to this, the energy density is virtually 0 with some small fluctuations. Then there is a large negative -1. That means the negative is 2 times. I'm shooting constantly here positive flux. Large negative means that it's 2 times higher than incoming positive. Then there is a region, what could be called wave localization, where the intensity of the wave decreases. Okay. Look at the densities. So this is density 1, and you can see that this was my density in front. And look how huge density fluctuations are. And again, this is for A0 10 to the -2. One expects that, and circularly polarized, highly underdensed. One expects of delta n over n goes as A0 squared. So one would expect 10 to the -4. But densities are 10 times, so they're 5 orders of magnitude larger. Wow.
So I have a question about energy conservation. I know this is Poynting flux, but it looks like there are a lot of stuff going behind. Right? So the energy is transferring from the pulse to density fluctuation. Reflected. More, very little goes into heating. It's mostly reflected. Yeah. So I cannot. The simulation block doesn't conserve energy because it is being reflected back, and it's killed at the left boundary.
Does it just escape the box like after
Yes.
it's been reflected?
Right. It's just escape the box just by the condition how the code treats any incoming wave, and well, anyway, it escapes the box. No, hold on. Yes. And circularly and linearly polarized behave the same. So again, normalization to 1 is circular, and then to 1/2 is linear. And again, blue is electron ion, red is electron positron. Electron ion behaves as expected. Electron positron first behaves as expected, and then killed. Again, dark region localization scale. Okay, and we interpret it as Anderson localization. And Anderson localization is a very broad term. that is related to behavior of waves in disordered media. And initially it was it was a quantum mechanical model of a transition from conductor to a dielectric. And roughly speaking, it's a diffusion, but with a phase. So one needs to keep not just it's not just the particle going back and forth. You need to keep the phase, to keep track of the phase. About the same year, Gertzenstein and Vasilyev showed that random dielectric reflects electromagnetic waves. And this is the same Gertzenstein who invented the LIGO concept, the Laser Interferometer Gravitational Wave Observatory. So obviously that person understood something about phase additions. So briefly, you might remember from your quantum mechanics course, say Dirac delta com or Kronig-Penney model. So if Dirac, if you have equally spaced delta functions, then what you have is a Bloch states, which kind of conduction bands. There are special bands, energy bands, where electron as a wave can propagate, and in other energies they cannot. For example, if you break off one pin, you can show that there will be always one localized state. Localized state meaning it goes to zero as we go to infinity. And roughly speaking, if we have now random these delta functions, all states become localized. There are no propagating modes. Okay? And here we are looking for, again, for the kind of, from the perspective of something that happens inside the medium. Okay, but the previous ones were a little bit different because those were the waves coming from outside. But Anderson localization has two kind of implications. First, a random medium reflects the waves coming from the outside, and it localizes waves that are already inside. Okay, the quantum mechanical electromagnetic correspondence both deal with waves. Okay, that's the analogy. The difference is Schrödinger equation is first, time derivatives, while wave equation is second. In steady state, they look very similar with a little subtlety. So this is my Schrödinger equation, this is my wave equation, and this is my random dielectric constant. The big thing here is that the fluctuating part is multiplied by the wave number, or the frequency. Meaning the strength, so this is the term, the random fluctuations that lead to localization. But multiplying by k squared means that it will, the source of localization will become weak at small frequencies, but at high frequencies, coherence will be harder to keep because you need to keep track of the phase to get localized. So we expect a range of frequencies, okay? And two electromagnetic effects of localization is again a random. It reflects electromagnetic waves, and waves inside random dielectric become localized. So here is what happens. We have a weak backscattered wave, and it arises from density fluctuations. So this is a nonlinear effect. This is nonlinear effect that feeds off little density fluctuations that become parametrically unstable, that is nonlinearly unstable. And parametric instabilities are typically much more dangerous than they're explosive. They can grow to infinite amplitudes and finite times. Most importantly, in pair plasma density sheets are charge neutral, and they quickly go nonlinear. Okay? And the dominant is two wavelengths per. So here is, for example, I do one single particle integration. So there are two wavelengths here, and I am shooting two waves and track particles, and you can see I get two density peaks per period. And this is a phase diagram, velocity of a phase, how particles behaves, and have a little, my peak colleague did the quick peak simulations that confirm this.
I'm sorry, what are the two waves that are propagating here in opposite directions?
Two waves propagating is in opposite direction. Two waves circularly polarized like this. I will discuss it. They will create, importantly, they create two bunches per period, and that corresponds to coherent Bragg's backscattering, meaning a wave that got scattered from here is in phase that, okay, the way is coherently adds up with the wave that got, oh, no, sorry, back. Adds coherently with the way, with every, but this actually picture is time dependent. So here is my snapshots of my density, and you can see that there is two density per period, then there is four, and so on. So you form a large density spike, and this density spike is actually logarithmically divergent. And that's the point, that I am driving it with very small amplitudes. Both waves have very small amplitudes. And yet I get logarithmically divergent density perturbations.
Okay. What do you mean by logarithmic divergence?
It goes as logarithm of x.
Log of x. So you have a counter-propagating wave, and then in the spike, you density fall off. It's logarithm.
At the spike, it rises logarithmically.
It rises logarithm. And then what's your units on the y-axis?
Density. Well, these are normalized density.
Normalized density.
Yeah.
One is like.
But this pattern is not stationary. So it spike, and then this one spike breaks into two. Then those two, okay, and then a new spike arises. So it's non-stationary, meaning it cannot be represented as a three-wave interaction, because there are many waves there, right there, and you see those spikes. These are huge spikes, and they're propagating in the wave in the plasma frame. Yeah.
What speed do they propagate?
They do this. I have a movie, but it's kind of not every half a period.
So the speed they move on is the Mach number.
No. It's pure. This is purely kinematic. This is
it's just speeding because
it's just purely kinematic. Yes.
Oh,
so yeah, it's this wave propagates a quarter of wavelengths every half a period.
So these waves. So is this like these three frames on the bottom panels? Is this like over time?
Yes.
So
this is it's about so this is 0. Oh, sorry. This is a 0, maybe period over 3. No, period over 4, period over 2. No, period. Hold on. 0, period over 4, period over 3, and period over 2 will be again. So it repeats every half a period.
I see. So I'm just looking at the y-axis. So it sort of starts off small, rises, and then falls again.
Yes. So yeah, and here are the single particle trajectories.
Mm-hmm.
So yeah.
Do you expect multiple peaks because it's a kind of interference pattern?
It's, as we see, this is quickly becomes a mess. Quickly it becomes a collection of randomly appearing large density fluctuations. And that's actually super important.
So it becomes like a continuum eventually, like it's like resonances piling up.
Well, you see that this is more or less time evolution. First, the densities are huge, then
I don't know how to quantify this. Yeah. I will soon have to switch to a laptop, but let's push on until it dies. Okay. This is my first project in peak simulations, and I did a lot of technical, well, a lot of testing. I started with cold plasma, but resolving the wire radius is very expensive, and I did it once. Nothing changed. There is minimal numerical heating. Also, self-localization depends on the fluctuations of the density. But the fluctuations of the density do depend on code resolution. And what is then expected is the onset depends on a square root of particle density. And here and the only solid feature in all my simulations is this kind of nose. And here I'm plotting the onset time of the onset depending on particles per on a number of particles, and I see a clear. Okay, hold on. No. I see a clear square root of independence. So it's not. It's another convergence. It's a convergence to the expected dependence on the resolution, square root, and this is actually from 3 orders of magnitude in resolution, from 20 to like 2,000 particles per cell. And
You have a 1D simulation?
1D, yeah.
And how does resolution get into this?
Because the effect depends on the fluctuations. And fluctuations depend on your number of particles per cell.
So it's a noise.
It's a noise. Yes. It comes from the noise, and level of the noise depends on the number of particles. And it's similar to many instabilities that, for example, Y-build develops from the noise as well, and that's how they test the code with Y-build instability.
Is the left-hand side of this supposed to? It looks very chaotic. So it like if I go to really, really low resolution, is it supposed to converge to a certain curve or high resolution?
High resolution increases. Well, this is the localization. Actually, those curves look very similar, and this is the localization. You can see that they start from 1, and they're all localized. Somewhat, yeah. It's hard to measure, for example, localization lengths because the fluctuations are very large, and actually they are predicted to be large, and that's what we see, that they're large at large localization depth.
I guess the question is, if you increase, say, system size and resolution, like, would you get a convergence in this pattern so that it,
like with any instability,
would be less and less as you,
this will be killed in a absolutely fluid limit.
of course.
So this relies on fluctuations. This is not a fluid instability. It relies, but this is the same as free electron lasers work. It's actually what I'm describing is actually a free electron laser, but in pair plasma. And in pair plasma, those density bunches are charge neutral. Otherwise, it's exactly like in a free electron laser.
Can you stimulate this by, rather than using noise, stimulate it for certain bands?
Yeah. So here what I do, there is clear prediction. So if there is a circularly polarized wave, and if I shoot another circularly polarized like this combination will produce density bunches, while this will not. Okay, so plus and minus. And here I'm looking at densities, plus and minus. This is exactly how I injected it. And this was for a long time, very long time. And you see these fluctuations are orders of magnitude larger. So this is and this is A naught 10 to the minus 3. So this is a very good test of the code, that it correctly predicts at this much weaker nonlinearity. It correctly predicts yes or no, meaning density fluctuations in the plus configuration and no density fluctuation in the minus configuration. And here I'm plotting energy density, and in the minus you see the precision is 10 to the minus 4. But here, even for this one, there is a little bit like 2% deep, because these density bunches, they start reflecting the waves that I'm shooting. So it's a very, it shows, and again, minor, really small A naught. So this is one of the tests that of the code, that it's at much smaller A naught, it correctly reproduces the expected results.
Why is it peak at the center? Why is it?
Well, I'm shooting the two lasers from the side.
So the timing sort of meets in the middle at the same time.
I think that's because the center felt the two lasers the longest.
So if you change the timing delay one, then it would shift one.
Something like that.
Okay.
Yeah, I think. Yeah.
And is your plasma thermal velocity small compared to the jitter velocity, even with this A naught?
There will be one on thermal. Okay. So then there is some theory. So what I did, for example, let's have 1D random delta layers of density layers. And then for each density sheet, all good?
Yeah, I can hear you now.
Yes, good. So I can calculate a scattering matrix for each delta layer, and then I randomly locate delta layers and calculate scattering transmission probability. And there is kind of one parameter, let's call it gamma, like the strength of scattering. And this is my transmission coefficient for amplitude, small t. And this is my strength of my scattering. And you see, when the strength reaches starts become of the order of unity, between 1 and 5, my transmission amplitude probability goes as 10 orders of magnitude. That means the transmission probability goes down as 20 orders of magnitude. And that's kind of, I think that's here I reproduce the classical example of Anderson localization, but for plasma screens. Okay.
So here the picture is nonlinear effects set up the density, random density fluctuations.
Nonlinear delta sheets of here they are the same, but they are randomly located.
So once that's been set up, this is a purely linear S matrix.
Right. So the wave falls in, and I do scattering from this. Then the wave acquires some phase, and then and then I set up there is no wave for it, and then I calculate the transmission for like 15 barriers. I cannot do more because it goes as correct. And also note, so this is one run, meaning I didn't average. And you can see that at large absorption, I have huge fluctuations. And that is indeed is expected of Anderson localization. Okay. So let us, what if a wave is produced in the region where first localization doesn't happen, but then plasma propagates and there is onset of localization. For example, this is different from this is astrophysically relevant laser regime, but it's different from laser experiment, and it's different mathematics because now we're looking at eigenvalues versus boundary value problem. What we did, and here is part of Victor did. So we start with a wave in the whole space, and then start growing randomly located delta layers. And we calculate normal modes of those new systems. So the system is a little starts to become time dependent, but if those density fluctuations grow slowly, this is a diabatic process. And here indeed, so what we see is, so this is a plot of eigenmodes of this newly created system. So at first it was just a wave everywhere in space. We see, so it's a bit, it's maybe a classical problem, but it's a bit different because it's something, the medium is changing in this case. And that's not the usual setup that is usually, usually there is some kind of sample that is already pre-manufactured. But here it's the medium that is changing. Number of quanta is conserved, momentum is taken by the medium. But if you remember, our medium is flying out relativistically. So though in the frame of the medium, it took all the momentum from the waves, but this is all flying relativistically, and in the end it will become transparent again, and the wave will escape. Next, we do a very interesting thing. So let's recall again our dispersion of a nonlinear wave in bare plasma. And the wave is superluminal. Okay. In a superluminal, you can go to what's called Klemov frame. In Klemov frame, the wave has zero wave number, no fluctuating magnetic field, and fluctuating electric field is spatially constant. And it is compensated by the current. So in that frame, you have electric field, which is rotating, and the particles that are rotating like this. That's the initial setup. Okay. I set this initial, and then I let it go. And what is plotted here in black is electromagnetic energy density, and in blue is plasma density. And you see that my plasma quickly separated into dense dark regions, high density, low electromagnetic, and bright low density regions. And of course, this is already non-linear stage, so probably this is already in the ponderomotive regime, not where phases doesn't matter, just ponderomotive averaging. But this is an example, a clear example how a wave will behave, which is already inside this Clembo frame. Then what I can do is as I run my simulation, I can plot the highest intensity at each point. The highest intensity in each domain, in the whole domain. So I start with 1. Then as waves become localized, the intensity within those localized bright regions increases. And again, this is just one run, and I see that over this localization time, the maximal intensity grew up to 5. But this is again one run, and I may imagine that if I were to make 100 runs, there will be one where the intensity would grow 100 times. And then there is a slow dissipation, very slow. It's a very long simulation here.
How is this different from the modulational instability?
1 or 2 slides from now on. Thermal spread kills the parametric, so temperature makes it transparent again. And the typical expectation is theta, which is temperature divided by mc squared, as a naught squared. And so at small temperatures, so this is 0, this is 0.1, 0.01, so it kind of behaves similar. But at 0.5, there is already clear evidence of transparency. And at 1, when the temperature spread equals the jitter velocity in the wave, it becomes transparent. And what happens is, as you form these little density fluctuations that will become then parametrically unstable, temperature kills those little density fluctuations. So the temperature competes not with the main effect, but with the growing little seeds, and it kills those growing little seeds. And then, what was that question?
Modulation.
Modulation instability. Yes, so here yeah. Okay. Usually so that's very right way. So we have a wave acts on itself. And usually those conditions those processes are treated as modulation instability, and there is Light-Hale criterion. And modulation instability is usually treated as expansion in small a naught. Then you get nonlinear Schrödinger equation, and all the parameters are expected to scale with some power of a naught. For example, density fluctuations in a circularly polarized wave are expected to go as a naught squared. And then this nonlinear Schrödinger equation is the equation for the evolution of the amplitude of the wave. Slow evolution of the amplitude of the wave. And actually, using this approach, circularly polarized electromagnetic waves and paraplasma were proven to be modulationally stable. Ours is a very different regime. We almost instantaneously develop very large density fluctuations, even for very small a naught. So this runs very contrary to the modulational approach. Many modes grow quickly. Modulation also usually can be treated as 3-wave interaction: the main wave, the perturbing wave, and a daughter wave. But here, as you saw, there is many density fluctuations, many waves, so it's not a 3-mode interaction. You can do a little bit of analytics, but I spend a lot of time on analytics, and it doesn't give you much. But you can show that your density fluctuations go as 1 over k squared. the amplitude, but the growth rate goes as k squared. So in some sense, largest small k, the winning wave, the wave that wins the nonlinear race has the largest small k. Okay, eventually the longest wavelengths would be the biggest ones, but before this linear regime, some intermediate wave becomes nonlinear and starts dominating the dynamics.
So in your previous slides, when you develop these bright dark density modulation, what set the length scale?
That's exactly what it is, I think. So this is it's related to the skin depths. It's like 5, 7, 10 skin depths.
Delta skin depths.
And there is no, and you see that they're a little bit different separations. And yes, that's my, yeah, this was actually my biggest, what sets the distance. And I think it's somewhat random. It's the when the nonlinear stage, when I cannot do any more linear perturbations. And unfortunately, I cannot do linear perturbations because I see that it doesn't reduce to a single three-wave equation. I immediately have many modes. I can separate the most fast-growing ones. They have the density fluctuations increase with small k, but their growth decreases with small k. So there is kind of some regime where the biggest of the small k's wins and become nonlinear. And actually, if you look at the time, sometimes these bright regions may emerge, but that takes very long time. Oh yeah, another very interesting thing. So I'm looking at this standing waves, and I'm looking at the polarization of these standing waves. And again, these standing waves are produced by a circularly polarized wave driver, and there is a circularly polarized backscattered wave. Okay. And then if I look at the polarization within this bright region. So here black is the intensity and blue is the polarization angle. And you see that within the bright region, polarization is constant. Polarization angle is constant. That means this pulse is linearly polarized. But this polarization, the position angle is random between different bright spots. So a circularly polarized driver created linearly polarized trapped linear trap electronic pockets.
So you have let's say you have a right-handed wave reflect become a left-handed wave.
Well, it's tricky because right-handed, left-handed depends. First, there is whether it's from the point of view of the source or the observer.
From K.
From K, yeah. So it's these waves that create density perturbations. These waves don't. It's these waves. And you do expect that the strongest backscattered wave will be of this polarization. So if this is the driver, the particles do like that, and they scatter a little bit backwards, and those backward will have this polarization. And this is exactly what is needed to create density structures. This won't.
So then why is it linear in pockets?
Because addition of two circularly polarized gives you a linearly polarized wave. The trick here that this wave first was very weak, but then in the nonlinear stage it became strong. And in nonlinear, this is what I observe. Yeah.
So if you start with a linearly polarized,
it will be linear, and it will be linear with the same. Yeah.
So it wouldn't jump over everywhere.
No, it will be linear the same. Yeah, I tried it, and nothing interesting. You start with linear and you get linear in the same. Yeah. Okay, we discussed that, and in the end, it's all Weibel, meaning
if you look in this Klemov frame, how particles move, they do something like this. And this is what I'm trying to. So the electrons and positrons, they move in a circle, and there is a current. There is a current at every point in space. And parallel currents attract. So then these currents start bunching up. And that's kind of Weibel instability. It's parallel currents attracting. So in this frame, it can be rephrased as Weibel instability.
But you need a 2D simulation for that.
No, it's okay. So if the wave is propagating in that direction, the current is in this direction, but it bunches along that direction. So it's in 1D. Oh, because it's 1D spatial, but 3D particle. Okay. One more point. There are, you can imagine, so there is this effect of ponderomorphic acceleration, meaning if the particle was at rest and a wave is coming in, the wave will push it. Okay. And as I said, our initial expectation was that we should follow this kind of sweep up. So basically, the parallel velocity should be of the parallel Lorentz factor should be of the order of A0 for large A0. But there is another regime. Since plasma reflects the wave, it absorbs the momentum, and that gives a snowplow push. Okay, the plasma reflected, and here is so A0 10 to the minus 1. And n over A0, and you see that the density grew up by a factor of 2, while the expectation would be 10 to the minus 2. That's why what I was able to do works clearly in a very narrow region of A0. Because for A0, as small as 10 to the minus 1, it's already messed. You see, and the plasma was swept up by 1,000 wavelengths. So it's already swept up, snow plowing swept up. So it's hard to interpret. 10 to the minus 3, it will take a very long time to develop there. So 10 to the minus 2 seems to be a sweet spot where things are still clear enough, large enough, and not too large. Okay. So somewhat surprising result that electromagnetic waves cannot just propagate in plasma. They are reflected from the boundary. Experience localization is insulated inside plasma. Guide field already will make it more normal, of course. And it'll be interesting to confirm this in the lab. There are some interesting, mildly strong waves self-modulate into brighter pulses that may avoid absorption or maybe erase periodicity. For example, if these are kind of astrophysical applications. I have more, but I definitely need to stop here. And thank you.